All right. Hey everyone. Today we are going to look at the most boring thing in all of functions. Personal preference, sorry guys. But we're going to look at transformation rules. So this is really important to understand your transformation rules for your functions and how certain things are going to affect the graph. But it is slightly on the boring side. So I apologize. Bear with me. This should be a really good review because you guys do a ton of graphing in Algebra 2. So these should really come to you really easily. If they do not, then you have calculators, right? So for the most part, we're basically going to be calculators for the next couple minutes while we do this video because it's just a bunch of graphing and graphing rules. So here we go, transformations. Where's my button? There it is. Okay, now I can slide over. All right, so this should look pretty familiar to most of you. I will zoom in a little bit. All right, so this great, beautiful equation that I have here, f of x equals negative a times f of negative b, blah, 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 whatever. This is your kind of transformation formatting. All right, so if you have f of x is our function. All right, the four things we're looking at here are a, b, c, and d. Now, every single year, someone says, Miss Lastly, what is transformation f? What is f doing? Y'all, f is the function. F for function. It doesn't do anything. It's just because we don't have a function in here, f is in there to represent said function. F is not a thing. It's not, you're not multiplying by f here. It's just the function. All right, now some teachers in Algebra 2 will write this a little bit differently. So you may have also seen this written like this. So negative a times f of x minus c over b plus d. Scroll over there. That's it. That's the whole thing. Okay, now this is really okay, kind of, in Algebra 2. This is not okay for pre-calc, not because I'm being picky, but we have a lot of functions where we don't write b in the denominator. It's not always going to be on the bottom. Most of the time, the b value is going to be out in front, like I have written in the, like typed up in the original equation. So it's really nice that you have your b value on the bottom in Algebra 2 because the only functions you deal with are very basic functions that are just going to have it on the bottom as a fraction, right? But we're going to deal with a bunch of functions that are going to have that b value pulled out front. Most specifically, our trig functions. All right, so I like writing it where everything is in a straight line, but like I said, you may have seen it written with b on the bottom in an Algebra 2 class. All right, so we're going to use this purple one because it applies to all of the different functions we're going to look at, not just the three easy ones that you guys dealt with in Algebra 2. Okay, so let's go back and talk about our different transformations. So we have three different types of transformations that we're going to look at in this class. We have translations, which these are shifts or slides. All right, so a translation, I like to think of these as slides. Slides, right? Your graph is sliding left or right. You can also think of it as like a shift. All right, but this is moving your graph left, right, up, down. All right, dilation, this is the transformation that is going to make your graph either bigger or smaller. All right, so this is going to change the size, right? This is actually the only one that changes the size. There's an E there, bigger or smaller, right? So dilation makes it either a bigger graph or a smaller graph, right? It can be vertical too, not just side to side, right? And then last but not least is reflection. So this is going to be a flip in your graph, right? So you're just mirror imaging, right? So I always think of reflections as flips. All right, so this is the one that's going to like flip it, like mirror image it, either side to side or flip up and down. All right. So like I said, out of all three of these different types of transformations, the only one that actually affects the shape of the graph is the dilation. Everything else is just changing the positioning of your graph, right? Whereas a dilation actually affects how big or small your graph is. All right. There's another transformation that we will look at later on this school year. It's called a rotation. So it's where we twist our graphs. We're not going to talk about it yet though, because twisting or rotating deals with angles, and we want to talk about trig before we get into talking about different angles. So we will definitely talk about that fourth type of transformation, which is the rotation, as we move into kind of towards the end of our school year. Okay, so let's just look at these three that we have here. So we'll start with translations. All right, so if we're looking at this beautiful formula that we have here, oops, I wanted to erase all my highlights. All right, we'll start with A. Nope, I lied. Let's start with D. D's easier. All right, so here we go. All right, so we're looking at this D value, and this is what's going to be our vertical translation. All right, so if D is positive, so if we have plus D, plus some number on the end, this is a vertical translation up by D. All right, so we are translating our graph up by however much D is. All right, so if it's a plus D, we move up by D. If it's a negative D, so if you have minus D, this is going to be a vertical translation down by D. Awesome. Next. All right, so our next translation is going to be the C value. All right, so C is our, what we call our horizontal translation. Now, these ones are a bit funky. If you remember this from Algebra 2, great. If not, then we're going to talk about it now. But whereas your vertical transformations, they always do what they seem to look like they're going to do, right? So if we add, we go up. If we subtract, we go down. If you multiply by a big number, you get bigger. If you multiply by a small number, you get smaller, right? It makes sense. Those are your vertical transformations, they make sense. Your horizontal translations, all of them, they do the opposite always, I feel like, of what you think they're going to do. All right, that's how I always kind of think of them. So if you have if you're subtracting C, all right, so if in your parentheses right there you have that minus C, this is actually going to be a horizontal translation. I'm going to like abbreviate this because translation is like such a long word. So horizontal translation to the left by C, right? So, oops, wrong, to the right. I thought I did plus first. I didn't, I did minus. All right, so if you have a minus C, you're actually moving in the positive direction, which seems backwards to me, but it is what it is. Which means if you have a plus C in your equation, right? So if C is like a plus some number, you're actually moving backwards or to the left by C. So this is a horizontal translation left by Z. So like I said, you're going backwards, which is so weird, but it is what it is. That's how translations work. Okay, so that is our two types of translation. So we have vertical and we have horizontal. All right, vertical translations are whatever D is on the outside, and horizontal translations are whatever C is on the inside of your function. All right, moving on to dilations. Now this is everyone's least favorite, so bear with me. All right, so the first one we're going to look at is, we'll stick with the vertical first. So let's look at A. All right, so if A, now first off, if A is positive, all right, so if we have a positive A, so A is greater than 0, so it's a positive whole number, all right, then you have a vertical dilation, or you would also say a vertical, this is what we're going to say anyways. We're not going to do dilation. All right, we're not going to do dilation. I'm going to tell you why in a second, but I'm going to write it. So you would say we have a vertical stretch by A. And we'll put it right there because this is like ugly. All right, a vertical stretch by A. All right, now the reason why I wouldn't say it's a vertical dilation is because you don't know what kind of dilation, right? So if I say it's a vertical dilation by 2, you don't know if we're making our graph bigger by 2 or if we're making it smaller by 2. So I like to use the words stretch and shrink when I'm talking about dilations, because it doesn't leave any ambiguity, right? You know that I'm stretching something, I'm making it bigger. If I'm shrinking something, I'm making it smaller. All right, so I like to use the word stretch instead of dilate, because when you just say dilate by 2, you don't know exactly dilating it in what way. Dilating it bigger by 2, dilating it smaller by 2. So I would prefer if you guys also use the terminology stretch and shrink when you're talking about dilations, because it gives a better idea of what we're doing. Are we getting bigger? Are we getting smaller? If you want to say vertically bigger by A, like, I'm not mad at it, but like, it just sounds dumb. I shrink and stretch, those are probably the better words to use. All right, now if A, so this is a stretch, this is going to make our graph so vertically stretched, so skinnier, right, taller. All right, and if A is, now not if A is negative, but if A is a fraction. All right, so if A is somewhere between 0 and 1. All right, so if the absolute value of A is somewhere between 0 and 1. We'll talk about why it's absolute value when we get to reflections, because that negative is going to do something different than dilate. It's not gonna dilate us, so we're really just looking at the absolute value of A here. All right, so if the absolute value of A is somewhere between 0 and 1, meaning it's a fraction. Fun fact, it's going to blow your mind. Did you know that there are infinitely many numbers between 0 and 1? What? Think about it. There is infinitely many numbers between 0 and 1. Just saying. All right. So anyways, moving on. All right. This is a vertical shrink. So if A is a fraction, it is actually going to shrink our graph vertically by A. So a vertical shrink by A. All right, so it's going to shrink our graph by a certain amount. Cool. All right, now let's talk about the next dilation, which is, we don't have any more highlighters. Oh no, what am I gonna do? I'm just gonna circle them. Okay. No, you should just highlight that. Okay, I'm just gonna add another one then. Add a highlighter. And we'll do this gray color. Why not? Who cares? Okay. So we're doing this B. Cool. Awesome. I'm into it. Okay. So looking at B. All right. So remember what I said a second ago when I said that it's going to always do the opposite? Same thing works with dilations. So if B is a number greater than 0, remember we're not talking about negative, so we just started looking at the absolute value of B. If B is a number greater than 0, right? So remember, we're not using this orange formula anymore. We don't like that because that makes it confusing. So just ignore that guy. All right, so we're looking at this formula. So if B is a whole number, so if it's on the top and it's a whole number bigger than 0, this is actually going to be a horizontal shrink by whatever B is. So remember, I said it always does the opposite when it's horizontal. So horizontal shrink by b. All right, which means if b is a fraction, so your b is on the bottom, right? So 0 is less than absolute value of b, less than 1. So b is somewhere between 0 and 1. It is going to be a horizontal stretch by whatever b is. Okay, so horizontal stretch by b. All right, like I said, anytime you're doing a horizontal transformation, it's always the opposite of what you think it's going to be, right? You think, oh, we're multiplying by a number bigger than 0. That's a whole number. It should make our graph bigger, but it's not going to. It's going to shrink you horizontally. It's going to make your graph look narrower horizontally, which I get this question every single year. Miss Lastly, isn't that the same as having a vertical stretch? No, the answer is no, it's not the same. All right. The only time where a vertical dilation can be replaced or exchanged with a horizontal dilation is in an absolute value graph. And if you think about that, right, think about a quadratic. If you're dilating by 4 on the outside, that's not the same as dilating by 4 inside the parentheses, because that 4, when you put it inside with your x, right, what's going to happen to it? It's getting squared. So the dilation's not the same. That 4 that you had on the outside, if you were to move it to the inside and just say it's the opposite type of dilation, it's wrong, because that 4 is going to become a 16 on the inside of the equation, right? So it is not the same. The only time it works is absolute value, because you're not doing anything to the numbers inside of an absolute value function. All right, and you investigate with your calculator. All right. Anyways, that's my rant. I get that every year, and every year I tell them, no, it's not the same. Dilating by 2 on the outside is not the same as a horizontal dilation of 2 on the inside. It doesn't work that way. Okay, last but not least, we're going to look at our reflections or our flips. This is what's going to come from those negative pieces. All right, so let's start by looking at the negative in front of the A. All right, so if A is negative, all right, so if you have a negative A, this is a vertical reflection over the x-axis. Okay, it's going to flip it like upside down. All right, it's an easy one. Reflections are always not too bad. What color haven't we done? Let's do red. Cool. All right, then we got this one, the negative next to the B. So if we have a negative B, this is a horizontal reflection over the y-axis, right? Which makes it go side to side. The y-axis is the one that goes up and down, so we flip side to side. All right, and that's it. Reflections are super easy. They're definitely probably the easiest ones. Their rules are the easiest to remember. So if you see a negative on the outside, know that there is a vertical reflection over the x-axis. If you see a negative on the inside, it is a horizontal reflection that will make your graph flip over the y-axis. Okay, now moving on to our next piece, which has to do with dilation. So if you took Algebra 2, oh no, what did I just do? Who knows? Stop it. I'm like breaking it. I'm not touching it anymore. I just need to touch it a little bit. There we go. Okay. So if you went to Ballard last year for Algebra 2, you should have learned about up-over patterns. If you didn't go to Ballard last year for Algebra 2, you probably have no idea what an up-over pattern is. I had never heard about it until I moved here, and I thought it was very strange, but it kind of is nice. All right, so we're going to go over it. So the 3 functions that you learned up-over patterns for were quadratics, absolute values, and square root functions. All right, what an up-over pattern is it's giving you, so it's basically saying starting at the vertex, okay, starting at the, okay, I'm not even touching that anymore. All right, let's just move the mouse all together. I don't know what's happening. All right, so starting at the vertex. Okay, we're all good now. Starting at the vertex, or your starting point of your graph, wherever you're at. So quadratics, it's your vertex. Absolute value, it's your vertex. Square root functions, it's like the first point of your graph. All right, we're just saying like starting at that first point. All right, some functions follow a pattern to plotting subsequent points. It's like a big word. I think I used that right. Don't judge me if I didn't. Okay, but now we're gonna have to go click over here somewhere. There we go. Okay. All right, so like I said, there were 3 functions that you learned this pattern for. So it was quadratics, absolute value, and square roots. All right, so with quadratics, the general rule is, so you start at the vertex, and then to get to your next 2 points, you go over 1, up 1. All right, so for the first point, you go over 1, and then up 1. Right, over 1, up 1. Put a dot. That's your next point. All right, to get to the next point, you go over 1, up 3. All right, so you do vertex, over 1, up 1. To get to the next point, over 1, up 3. All right, and then to get to your next point, you're going to go over 1 again, but this time you're going to go up 5. All right. Now, the reason why that's important to know is because when you do different dilations, it affects this over-up pattern. All right, so the overs are getting affected by any horizontal dilation. All right, so over is changed by horizontal dilation, whereas the ups, because they're vertical values, up, so up is changed by vertical dilations. All right, so you're just going to multiply. So like if you had a horizontal dilation of 2, right, you would take all of your over values and you would multiply them by 2. So instead of going over 1, you would go over 2, up whatever, over 2, up whatever, right? If you have a vertical dilation, you take that dilation amount and you multiply it by your up values, each one. So say you had a vertical dilation of 3. Well, to get to your first point then, you would go over 1, up 3. To get to your next point, you would go over 1, up 9. To get your last point, you would go over 1, up 15. I'm trying to do math in my head. All right. So those are your dilations. All right. So moving on to absolute value. This one is pretty easy because nothing's really happening. So your pattern is just over 1, up 1 for literally every point. It just goes over 1, up 1. So over 1, up 1, over 1, up 1, over 1, up 1. It's really boring. Absolute value graphs are like super boring. All right. And the same deal here, right? Over is being changed by any horizontal dilation, whereas up is being changed by any vertical dilation. All right, and that leaves the square root function last. Now the square root function and the quadratic function are inverses of each other, right? The opposite of squaring is square rooting. So these ones work just in reverse. All right, so the square root function is going to be over 1, up 1, over 3, up 1, over 5, up 1. So it's just the reverse of the quadratic rules, all right? And that's how you do your square root function. Okay, let's move on to our example. Boop-a-da-boo. Okay, oh, my head is like really in the way. We'll move it. Look at this, I can just bloop, bloop. Now I'm up here. Look how fancy I am. Okay. So this says determine the parent function of g of x, describe the transformations that occurred and the new domain and range, graph the parent function and the transformed function. So look at all this stuff we have to do. Okay, so first things first, what is the parent function of this thing right here? Well, there's a square root up in there, so it's probably the square root function. Ding, 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 you're correct. All right, so parent function, this is the square root function. Square root function. Excellent, that was easy. All right, so now what I'm gonna do, I'm gonna go ahead, I'm gonna graph my parent function right now. Right? So your square root function, if you don't know what this looks like, this is f of x equals the square root of x. All right, so you can either know what this looks like in your brain, or you can go to your calculator, graph it, and then plot this. So I'm going to go ahead and just plot this on my graph right here. All right, so it starts at 0, 0, and then it follows the square root pattern, right? We said over 1, up 1, over 1, 2, 3, up 1, over 1, 2, 3, 4, 5, up 1. All right, this is the parent function. I'm calling him f of x or her or gender neutral, it doesn't matter, right? I'm calling it f of x. All right, next, I'm going to go ahead and I'm going to describe my transformations that are happening to my function. So I'm going to start with any translations that are happening. So if I look at my function, I see that I have a +3 inside the function. Well, anything that happens inside the function is a horizontal transformation. All right, so maybe remember that, right? So inside the function is always a horizontal transformation. If it's on the outside of the function, it's a vertical transformation, right? So if you go back up to the top and you look at any of our, I don't want to, my head's all up in the way, right? So look at the things that we called vertical transformations, right? D is vertical, A is vertical, and the negative A is vertical. Those are all vertical. Those happen outside of the function. Whereas everything that's a horizontal transformation happens inside. So B and C, both of those happen inside of F. So inside of our function, all right? And that's always the case. So if it's a horizontal transformation, it's going to happen inside. If it's a vertical transformation, it's going to happen outside. All right. So here we go. Now I need to move my head. Okay, there's my head. Okay, cool. All right, so let's figure out a transformation. So we said we have a +3 and it's on the inside of the function. So that is going to be horizontal. All right, so first thing I can put is horizontal. All right, is it a dilation, a translation, or a reflection? It's a translation. So horizontal translation. All right, are we going left, right? Well, it's a +3. Remember, horizontal always does the opposite of what you think. So +3, you think usually it's going in the positive direction. You would be wrong because remember, horizontal is always dumb. It's backwards what you think it's going to be. So really, we're going to the left. We're going backwards. All right, so horizontal translation left by 3. Excellent. All right, what else is happening? Well, if I look at my thingy here, I see that I have a 3 on the outside. So I'm not looking at the negative yet. So I have a 3 on the outside. So if it's on the outside, I know it's a vertical transformation. And it looks like we are multiplying by 3. So if we're multiplying, that's going to be a dilation. And since my number is bigger than 0 and not a fraction, I know it's going to stretch my graph. All right, so I have a vertical stretch by 3. Cool. All right, and then last but not least, I also see that there is a negative out front. This negative is happening on the outside, so I know it's some type of vertical something, right? So it's vertical something. and it's a negative sign. So that's going to be a reflection. So it's a vertical reflection. All right, now you can just write vertical reflection, or some people like to get really specific and say vertical reflection over the x-axis, but there's only one kind of reflection. It can only just go over the x-axis. You can't reflect vertically over anything else. So if you have the vertical reflection piece, that's enough. I know what that means. There's no alternate thing, right? It's not like a left or right situation. It's only one direction it's going to go. So I'm cool with just vertical reflection. All right, let's go ahead and graph that. All right, so we're translating left 3. So we're picking up our graph and we're moving it left 3. All right, so that means my starting point is going to be backwards 1, 2, 3. All right, there's my new starting point. All right, I also have a vertical reflection, so I know that I'm going down, right? So I'm gonna, when I plot my points, I'm going underneath of that line right there. All right, and I also have this vertical stretch by 3. So if you go to your, I'm gonna move my head because now it's right up in the way. All right, so we have a square root function right here. All right, and for this one, we are multiplying all of our vertical values, so our up values, by 3. So I'm just going to times 3 here, times 3 here, times 3 here, which is going to be 3, 3, 3. All right, so now I can use this up over rule to figure out my rest of my points. All right, so from here, I'm going to go, instead of up, I'm going to go down, right? Because, you know, I am where I am. All right, so we have over 1, down 1, 2, 3. Over 1, down 1, 2, 3. Over 1. Nope, I just did that wrong. It's okay. Over 1, 2, 3, down 1, 2, 3. Over 1, 2, 3, 4, 5, down 1, 2, and oh my, 1, 2, and 3. Bam. This is g of x. It's beautiful. Sorry, I had a counting issue there. Okay, so now let's look at our new domain and range. This is the last thing that we're going to do. We're not going to do that example down there because I don't want to do it. It's been too much time. We're already at 32 minutes. Oh my God, I'm so sorry. You're going to need to watch me on speed up, 1.5 speed. Okay, so new domain and new range. All right, so remember we said domain, this is what x cannot be. All right, we know that whatever is inside, underneath that square root cannot be a negative number. All right, but we can also just look at our graph, right? Look at where x's start, right? We don't have any x values on this side of that point. All right, our first x point is right there at -3. So for our domain, we're starting at -3, and then we're going in the positive direction of the x-axis forever. So positive infinity. We do touch that point -3, so we're going to use a bracket, and we never touch infinity, so we use a parentheses. All right, so that is domain. Let's check out our range. So ranges are y values. All right, well, we are coming from the bottom, right? So we actually touch, we have all of these y values, right? We touch all of these y values. But we stop right there at the y-axis. So, or sorry, the x-axis. It's been a long day. All right, so our range is, our smallest number is -infinity, right? Because we're coming from the negative numbers. We go down for forever. All right, and a parentheses because we don't include infinity. All right, but then we go all the way up until we hit that point of our graph, which is sitting on the x-axis. So it means our y value is 0. And we do touch that point, so we would use a bracket. That is it. All right, so that is transformation rules. I know that was, like I said, a bit lengthy. I had no idea we were at 30 some minutes. So I apologize, but I hope it was informative. I hope it refreshed your memory on transformation rules. So yeah, I hope that you are now able to complete your homework. And if you have any questions, I'm available during asynchronous time. Just saying, I get really lonely. Come visit me. All right, bye guys.